So in this topic, we're going to talk about magnetic fields. Remember, magnetic fields can be produced when there is a moving charge, when there is a moving flowing current, or when there is a permanent magnet. So you realize that the sources of the magnetic field will depend on the presence of a moving charge, permanent magnet, because if you have a magnet here, have a magnet and another magnet, let's say North Pole, South Pole. Let me use a South Pole here, then a North Pole here. Then we're going to have magnetic fields which are going to be repelling each other. Yeah. So we shall say those are the sources of magnetic fields. Then the properties of this magnetic field is that they always point from the North Pole to the South Pole. You need also to remember that they never cross each other, and where they are very close, that means a region like this one where they are very close, it means there is a stronger magnetic field. So the density implies the strength of the magnetic field. We are going to also look at force experienced when a magnet the force a conductor experiences when it's placed in a magnetic field and there is a flowing of current. So a force on a current carrying conductor, this force will only be produced under the following condition: current must be flowing. That's one of the conditions under which this force is going to be produced. So the condition under which this force the conductor that is carrying current is going to experience will depend on the following. Number one is the current must be flowing. The current must be flowing for this force to be experienced. Current has to be flowing. You need also to remember that the current should not be parallel to the direction of the magnetic fields. Current should not flow parallel to the direction of the magnetic fields. We can say there is maximum amount of force when the angle between the field and the magnetic field and the conductor is 90 degrees when they are perpendicular, but there is zero force experienced when the conductor is parallel to the field. So the force we are going to say when you are asked to calculate the force experienced is the strength of the magnet, that is the magnetic flux density. B is the magnetic flux density times the current in the conductor times the length of that particular conductor, then sine angle. The sine is the angle theta is the angle between the conductor and the field, but most of the time we are applying this when the angle is 90 degrees, and then you are going to get maximum amount of force. All right, so anytime you are asked to calculate the force experienced by the conductor that is placed in a magnetic field, you are going to use Bill formula, which is the magnetic flux density times the current times the length of that particular conductor that is in that magnetic field. So for instance, if we are talking about this conductor, our length will be the length of this in meters and the amount of current, and then the magnetic flux density of these fields, electric fields that we are having. The magnetic fields that we are having here going to be B. Yeah, so that is about magnetic fields and the force experienced by a conductor that is placed in the magnetic field. That is how you're gonna approach that. And if you are new to Proflan YouTube channel, consider subscribing so that anytime I'm going to upload more tutorials, you'll be notified. And I would like to remind you that if you want to download this document that I'm having here, I usually add this document in our Patreon page so that you can be able to access it. Let me just position this paper. It's gonna tear in before I upload it to you. Let me just rearrange it. There's one part here that's gone out. So release this. Yeah. So that is magnetic fields and the force experienced by a conductor that's placed in the magnetic field. So the stronger the magnetic field, the greater the stronger the force, or the greater the force. And also we have the length within the magnetic field. Now the next part that we're going to move is when a charge is placed in a magnetic field. When we're talking about a charge that is placed in a magnetic field, it also experiences a force. Yeah, and this particular force it experiences can be determined by Fleming's left-hand rule, or you can use right-hand palm rule. Yeah, so you need to remember that the force a charge that is going to experience in a magnetic field will be the magnetic flux density times the amount of that particular charge that is moving within the magnetic field times the speed at which that charge is moving. So if the charge is moving very fast, it means it's going to experience a greater and a stronger force. So the force is maximum, as we mentioned, when theta is 90, and the force is 0 when the angle is 0. Yeah. So there's something also we call Hall effect. So if you put a conductor inside a magnetic field, remember there will be as we have seen from here, is that when a charge is placed in the magnetic field, is going to experience a force, and when it experiences a force, it can be able to deflect. Yeah, it will deflect. It will experience a force and it will move, meaning it can deflect. So if a conductor is carrying current and that conductor is placed within the magnetic field, remember current is a flow of charge. So when current flows through a conductor and that conductor is placed in the magnetic field, the charges in the conductor are going to experience a force and they are going to be deflected. And when there is a deflection, a potential difference is going to be created across the conductor. So you need to remember that when a conductor carrying current is placed in the magnetic field, the charges in the conductor are going to experience a force due to the presence of the magnetic field, and that is going to cause a deflection of the charges. So the charges are going to be deflected in a way that their direction is going to change, or their orientation in which they are moving the conductor is going to be affected. And when there is a deflection of charges in a conductor, that is going to create a voltage, and that voltage is now what we call the Hall effect voltage. And this Hall effect voltage, Hall effect voltage, is going to be equal to be the magnetic flux density times the current of that current that is flowing the conductor divided by the number of charge density times the charge, and then we have the thickness. T is the thickness, so meaning you are going to use this particular formula that we are having here in order for us this formula here for us to calculate that particular Hall effect voltage. So something also that you have to put into consideration and is that when a charged particle is placed within the magnetic field, it's going to experience a force. So if we have a positive charge placed in a magnetic field like this, it's